What you're looking at right now might be one of the most important frames ever captured on Mars. Mainstream science says it's just a normal hill, but by the end of this video, you will see exactly why the official story might not be true. So, with that said, here we go. Take a good seat, and let's discover together the secrets lying here on Sol 1272. They tell us the landscape of Gale Crater is entirely shaped by standard Aeolian processes, wind blast effects, thermal stress fracturing, and ancient, long-dead seismological activity. It makes sense on paper. But when you actually scan the raw data, that standard geological explanation becomes a legitimate mystery in itself. Let's establish the stakes. When we talk about mechanical weathering on Mars, we expect predictable results. We expect rock formations smoothly planed down, pitted, and aerodynamicized by continuous, unidirectional winds carrying abrasive basaltic dust. We expect regular, random cleaving from intense day-to-night thermal cycling, where temperatures swing wildly by over 100 degrees. This massive thermal shift causes the outer shells of these rocks to flake off over millions of years. But the raw data from Sol 1272 completely distorts that standard model. We are seeing specific structures right on this slope that seem to reject random physics entirely. Let's dive straight into the raw pixel data and look at the first target. The first anomaly sits right on the mid-slope of the ridge, surrounded by fine-grained basaltic drift sand. Mainstream geology would classify this as typical sedimentary layers, perhaps mudstone or cross-bedded sandstone, from ancient lacustrine environments exposed by wind erosion. But look closely at the sheer thinness and hollowed-out curvature of these plates. Standard thermal cycling usually causes Martian rocks to split along parallel bedding planes, creating flat, predictable fractures. Instead, the Sol 1272 data shows ultra-thin, overlapping sheets forming enclosed, hollow cavities. It looks less like a standard rock fracture and more like a hollow tube or pipe, featuring distinct, parallel lines running straight down the side. Look closely at the left side of the structure. There is a specific, geometric pattern embedded directly into the form. How does wind blast erosion selectively hollow out the interior of a solid boulder while leaving paper-thin, overhanging rock shelves completely intact? It defies the known fluid dynamics of Martian sandblasting. If abrasive, unidirectional winds carved this out, these fragile upper shelves should have sheared off a long time ago. Now, hold that thought, because as we trace this feature further down the slope, the geometry becomes even more difficult to explain. From a distance, the crater slope shows very little to disrupt the standard geological narrative, but as we focus the pixel data on the top of the ridge, the expected randomness of mechanical weathering completely breaks down. Look at this first structure. It is a highly distinct, cubic geometry. Standard fracturing leaves flat faces, but this feature is entirely hollowed out. Mainstream models attribute this to a combination of wind blast, radiation, and ancient fluid erosion. Yet, how do those chaotic forces carve sharp, orthogonal corners into a hollow cube? Moving further down the slope, we encounter an object that directly defies typical basaltic fracturing. It appears as a tight cluster of individual tubes gathered together to form a distinct, cylindrical shape. Mainstream geology would search for analogous terrestrial structures, like volcanic basalt columns, but those require specific, large-scale cooling conditions not found in this isolated strata. This feature is entirely unique to the immediate area. If this is standard erosion, where are the other examples? Continuing down the hill, mastcam data reveals a precise, shallow boxwork layout. We see straight lines and regular right angles forming interconnected cells. Geology blames cross-bedding or resistant mineral veins surviving host rock erosion, but this symmetry is fiercely precise. Is it just compliant erosion or an entirely different mechanism? To test that theory, we have to pause and measure these anomalies against a real baseline of Martian wind erosion. If we saw just one isolated boxwork layout or one hollow cube, we could archive it as a geological outlier, a freak accident of chaotic wind and thermal fracturing. But forensic analysis isn't about single anomalies. It's about probability. Why is this specific ridge defying standard environmental physics? To understand the contradiction, look at the green hue pediment on Sol 3415. This is what relentless wind erosion actually looks like when it dominates a Martian landscape. It plows massive, parallel grooves into the bedrock, carving wide fields of scaly, streamlined ventifacts that all face the exact same directional wind pattern. The forces are chaotic, but the physical results are uniform. So why? Back on the Sol 1272 ridge, are we seeing the exact opposite? Instead of wide, uniform, sweeping wind channels, we are seeing localized, paper-thin hollows and right angles that completely ignore the wind profile. The standard model is becoming harder to defend than the geometry itself. Keep that mathematical improbability in mind, because what we find next completely shatters the erosion narrative. Look at the lower slope of that ridge. We can see a heavy dispersion of stones and debris, fragments certainly cleaved from the upper strata over deep time. Mainstream geology views this as a standard tailless slope, a random graveyard of falling rocks. But let's zoom in and look closer at the pixel data, because buried within this chaotic field of rubble are shapes that don't belong in a random rock fall. And this is where things start to get very interesting. Look closely at the lateral face of this single stone. Right here on the side, we see a highly localized, deeply etched signature scoring the material. It consists of perfectly parallel, horizontal lines bounded by a sharp, clean vertical edge. Mainstream geology blames standard differential weathering on layered sedimentary strata, claiming softer layers simply eroded faster. Aside from this fragment, look at the surrounding area. We can see other anomalies close by, but they feature completely different shapes and aspects. And that's the thing. It pulls us straight back to the core contradiction. If uniform wind erosion is the sole architect here, it should produce uniform results across the same rock strata. Instead, we are looking at total randomness in shapes mixed with precise geometric digressions that completely break the mainstream erosion model. Now, hold that thought, because these localized anomalies present completely different geometric profiles. We are looking at sharp, linear alignments directly adjacent to right-angled knobs right next to anomalous rounded structures. It makes no sense. If a single environmental force like wind or thermal stress was the sole architect here, the morphological results across this specific hillside should be uniform. Instead, it looks exactly like a forensic crime scene. A highly chaotic debris field containing the shattered structural evidence of an event that occurred down in deep time. And for whatever reason, mainstream models are ignoring it. When you look at the pixel data through this lens, the role of Martian wind changes completely. Erosion isn't creating these shapes. It's slowly obliterating and covering them up. So we have to pull back and ask the ultimate question. Could it be possible that something the mainstream narrative labels as completely impossible actually happened here? Are we looking at highly selective, compliant geology that defies the laws of physics, or the heavily eroded remnants of an engineered reality? Keep that question in mind, because the final target on this ridge completely shatters the erosion model. Look directly at the exposed rim of this upper cliff face. Right here, embedded in the bedrock, the pixel data reveals two highly symmetrical, squarish cavities carved directly into the stone. Mainstream analysis remains completely silent on this target. There is no official answer. Standard geology attempts to blame selective pocket weathering or regular joint fracturing, but the geometric symmetry between these twin hollows is fiercely precise. But that's the thing. Wind and thermal stress do not selectively hollow out matching sharp-angled boxers side by side while leaving the surrounding matrix completely untouched. Make it make sense. With all of this said so far, the standard erosion model simply cannot explain this level of structural organization. It is becoming an artificial shield used to protect a comfortable, sterile narrative. To be crystal clear, we aren't claiming to have the final answer, just as we still struggle to understand the precise engineering behind the pyramids on Earth. We must accept that Mars is harboring structural secrets older than human civilization itself. The data is raw. The geometry is undeniable. Trust the pixels or trust the compliant models. If you want to follow this ongoing forensic investigation, leave a comment with your theory below. Smash the like button and subscribe to the archive. Stay sharp and wait for the next video.